This is a satellite foundational course for JPSS, the Joint Polar Satellite System. This module discusses ways to use VIIRS imagery from SUMI NPP and NOAA 20. I'm Scott Lindstrom from SIMS. VIIRS has superior spectral and spatial resolution to GOES-R's better temporal resolution. This is especially true as you move toward the poles. In addition, VIIRS includes a day-night band that allows visible imagery at night. This list shows what is discussed in this training. This short list will be expanded upon in the future. If you find a novel use for JPSS data, let us know. Light from the sun or from the moon can reflect off water. The bright region of sun glint or moon glint in satellite imagery can be used to infer surface or subsurface properties. In this example from AHI, you can see internal waves in the ocean in regions of sun glint. An animation of this image is available at the link shown. For geostationary satellites, this works only near the equator. But polar orbiters can detect sun glint or moon glint in the day-night band in mid-latitudes or near the poles. Read more about this at the reference listed. Differences in moon glint or sun glint in this case can be used to infer the state of the lake surface or sea surface. When there are wind-driven waves, reflection is in all directions and water will look gray. Where the lake surface is flat because there is no wind, reflection is mostly in one direction and the water is darker. In mid-latitudes, the position of polar satellites with respect to the sun and the observation point allow these dark patches to be observed, as shown here with a Terra Modis visible image. A view of this image from GOES 12, then operational as GOES East, showed no dark patch in Lake Michigan. So this dark region is a region with no wind. And a wind analysis confirms that. It's not just visible reflectance that's affected by the sea state. There is less 3.9 micrometer reflectance in the calm region as well, so the inferred brightness temperature is cooler than the adjacent regions where there is more reflectance of solar radiation. If there is no reflectance at all, the 3.9 micrometer brightness temperature in the calm region would be close to the actual emitting surface temperature. If there is no wind, there is no mixing of water. This allows a thin film of water on the surface to warm up. Observed sea surface or lake surface temperatures will warm considerably compared to adjacent regions where winds will mix warm surface and cooler subsurface waters. Moon glint works just as well as sun glint in identifying regions of calm. Note that the moon glint also casts shadows. You could use those shadow lengths to infer cloud height over the western Gulf of Mexico. Day-night band visible imagery can also identify low-level circulation centers at night. This is very handy for tropical cyclones if sheared systems have deep convection very much separated from the low-level circulation. You really do need to know where the surface center is when initializing forecast models. Here is an infrared image of a tropical system that is east of Hawaii. The precise location of the storm is vital for its insertion into a numerical model. Where is the center? Did you place it where the X is? It's pretty simple to see the circulation in the visible, at night, day-night band image that comes next, but it's difficult to infer its location from this infrared imagery. It's not uncommon for sheared systems to have a circulation displaced from the main convection. The day-night band visible imagery with ample lunar illumination reveals the low-level circulation. Here's another example. Where would you expect the circulation center to be in this infrared window image from VIIRS? Did you imagine the circulation center to be where the X has been placed? But the day-night band visible image reveals a distinct low-level swirl in the clouds there. This is the center of this sheared tropical system. Here are two images of Tropical Storm Bonnie from 2016, the infrared and the day-night band visible imagery. The low-level swirl that is the center of sheared Tropical Storm Bonnie is masked in the infrared image by cirrus clouds above it, but the cirrus is thin enough that it's easy to find the center of the system in the nighttime visible. Also, again, note the shadows from the convective towers on the moon glint. You can infer convective cloud heights from this information. Here's one more example of a sheared storm. In this case, only Earth glow is illuminating the cloud field, and you can still find a circulation center. Note also the streaks of lightning in the deep convection. Lightning shows as a streak because it is detected as it is occurring in just one swath. When VIIRS was scanning poleward and equatorward of the lightning location at slightly different times, the lightning was not occurring. In visible wavelengths, land is not very reflective. You know this because it appears quite dark in visible imagery. Land is a lot brighter in the near-infrared. There is more reflectance from grass and dirt compared to the visible in the 0.86 and the 1.61 micrometer bands. Thus, vegetated features and bare ground will appear bright. This is important because water is dark, and the contrast between bright and dark means flooded regions can be better identified. This example shows flooding on the South Platte River in Colorado shortly after torrential rains hit Boulder. The contrast between the reflective land and the river water is very distinct. If you're familiar with the region and know what the river usually looks like, that is helpful in interpreting the scene. A bonus scene occurred on this day. This region benefited from two sequential passes about 90 minutes apart. So you could see the progress of the flooded crest in those 90 minutes and maybe even calculate its speed. It's a few days later. How far has the flood crest moved? Of course, clear skies help. Here's the view on the 17th. The flood has almost reached Nebraska. VIIRS data can be used to create an inundation product as well. And this image from October 11, 2016 shows inland flooding related to Hurricane Matthew. VIIRS has higher spatial resolution imagery than geostationary satellites. This is especially true as you move to higher latitudes. VIIRS is therefore better positioned to detect stratus and fog events in narrow valleys. The day-night band can give you information in the visible about the horizontal extent of the stratus, and the infrared can as well, by exploiting the emissivity differences at shortwave and longwave infrared channels of water droplets as found in stratus clouds. The brightness temperature difference field here shows fog and stratus starting to appear in the river valleys of southwest Wisconsin. It's not quite yet on the Mississippi River, however. VIIRS can give an early alert to the formation of fog if the overpass is timed right. GOES imagery from the next morning shows more widespread fog. VIIRS has high spatial resolution, and if you have narrow valleys or sharp edges to the cloud bank, you are better able to describe exactly where the fog is present. You've already seen a flood monitoring case where data from sequential VIIRS passes overlapped and gave useful information. Such overlap is most likely at higher latitudes. The presence of multiple polar satellites means that VIIRS, from SUMI NPP and NOAA 20, for example, or from other satellites, such as MODIS in this example, can be combined to give multiple views of the same scene to determine the evolution of weather at high spatial resolution. Look at the fog in this image. Compare that MODIS image to the same scene from SUMI NPP, another polar orbiter, 2 hours later. The fog is advancing down the Salinas Valley. Less than an hour later, AquaMODIS views the scene. If you know when polar satellites are passing, you can realize high-resolution imagery for features. Visible imagery at night, that is the day-night band on VIIRS, will view fog, clouds, smoke, and city lights. You can see fog in the valleys of southwest Wisconsin here. Is there any fog over Chicago or Minneapolis? The lights of the city make it hard to tell. Is the feature spreading southeastward from the northwest corner smoke, cirrus, fog? You should interrogate other channels or products to discern that. In this case, the brightness temperature difference shows stratus clouds over the river valleys of Wisconsin and over Chicago. The Twin Cities show no fog detected. Smoke is not detected in the brightness temperature difference field, but cirrus is. So that feature spreading southeastward from the northwest corner is probably smoke from forest fires. Smoke detection at night is something the day-night band that you just saw, when there is sufficient illumination, excels at. When you suspect fog at night and see a signal near cities in the day-night band, the infrared imagery, specifically the brightness temperature difference, can help distinguish between fog and stratus and city lights over metropolitan areas. VIIRS imagery detects fires. There are multiple shortwave infrared channels that can be used, and some have excellent horizontal spatial resolution, meaning small fires are detected. Smoke from fires shows up in the day-night band. Here's an example from the Fort McMurray fires over Alberta in 2016. This is at 56 degrees north latitude, far from the GOES sub-satellite point. GOES 16 pixel size here exceeds 5 kilometers, so small fires cannot be detected well. In this case, the fires were widespread and large at this time, but VIIRS better describe the horizontal spread of the fire. In addition, the day-night band ably characterized the horizontal spread of the smoke pall, an important piece of information for air quality alerts. Here's the GOES East imagery for about the same time. Only 1 pixel is very hot, and there's no information about smoke. 1 week later, VIIRS sees smaller in area, fires that might not be perceived by GOES. The moon at this time is not providing sufficient illumination to show where the smoke plume is, but the visible light emitted by the fires is obvious. VIIRS data are more likely to detect fires that are small in size, in this case over Idaho. There is both a thermal signature in the infrared and a visible signal in the day-night band. The day-night band also shows the smoke. Here's another example over California. The thermal signal is readily apparent, and the horizontal extent of the smoke offshore is captured nicely. It can be trickier to monitor where the smoke is if it drifts over city lights. True color imagery from VIIRS depicts the smoke very well during the daytime. In addition, there are smoke and fire-related products, such as aerosol optical depth, that's available during the day. After the fires, VIIRS data can be used to detect burn scars at night. This is a post-grass fire burn over Kansas. There is a difference in reflectivity that the day-night band can capture. During the daytime, of course, you can use the 0.86 micrometers to see burn scars. Compare the day-night band imagery to the GOES 16 0.86 micrometers from the day before. In this case, there was no cloud-free daytime VIIRS view of the fire region. Remember, VIIRS data on SUMI NPP and NOAA 20 has much better spatial and spectral resolution, and it complements GOES 16's and GOES 17's better temporal resolution. Use them both. In particular, VIIRS has a day-night band that produces visible imagery at night that can help for a variety of situations. That band nicely complements other infrared channels on VIIRS to describe weather in the scene you are viewing. This concludes this short training on how you can use VIIRS imagery. Thanks for listening.